In this talk, we will show you how to automatically lay out shapes, like in this example, and we will explore applications in vector graphics and beyond. To achieve this, we will have to define energy that will ensure that two given shapes don't overlap. And we want this energy to be differentiable with respect to different parameterizations of the shapes. We want it to be defined on different shape types and be robust to any initialization. So it may sound like a simple problem, but even just for rectangles, we posed this problem publicly and got a lot of responses with many nice ideas for how to define such energy. But it turns out that all of them either fail for some specific initial configuration of states, or they don't generalize beyond rectangles, or they are just not practical to compute. So instead, in this work, we propose a method based on Minkowski differences, which works for all of these initial states with rectangles, and also generalizes to other shapes. And more precisely, we use simple observation from collision detection, which says that two shapes, A and B, are overlapping precisely when their Minkowski difference contains the origin. But this is just a binary indicator, so to create smooth energy from this, we use the sign distance field of this Minkowski difference and evaluate it at 0. And with this functional, we can define all of these different penalties that ensure constraints like no overlap, tangency, and even containment. Now, Sam will tell you how to actually compute this.
Yeah. So the way that we do this in practice, we can work out closed form solutions for a lot of different things, even including like Bezier curves, even ellipses if you're willing to deal with high degree polynomials. But what we do in practice is we just approximate any given shape or curve with a polygon by sampling points from the curve itself. And then we apply an algorithm called reduced convolution from the prior literature to compute the Minkowski sum of two polygons. This works for any pair of simple polygons. The robustness is a bit tricky in practice. We implemented an implementation in Rust that works pretty well for our cases, and then we use random perturbations and for like certain cases, like if the polygons are axis aligned or like identical polygons, you sometimes need perturbations for this. In particular, if you have two polygons that are only going to translate around, then you can use a shortcut where you just pre-compute the Minkowski sum and then you offset it using the translation point. So this is what we do for a lot of our examples, and it really speeds up the optimization so you don't have to compute the Minkowski sum in the loop, which would be cool for future work. This works really well in practice for the polygon approximation because even if the shape is not exactly right, typically we want to preserve some sort of padding, like two shapes are disjoint, but they also have like a little bit of a gap between them. And the more padding you add, the better your polygon approximation actually works. So you don't usually notice the difference in practice because you have these gaps between shapes, whether they're contained or whether they're disjoint, etc. But yeah, so these are not super easy to compute. This is what you get from the reduced convolution algorithm. To do this, we work out an implementation of the Minkowski sum that we differentiate by keeping track of the relationships between the points from the original polygons in the final Minkowski sum. So for instance, there's like kind of a few categories. You can have 2 points that are a sum. You can have 2 points that are an intersection of segments that were summed from the original polygons. And that's kind of like the only categories. So you just remember how each point came from the original polygons, and then when you differentiate, because we're taking the sign distance from the origin, we only care about one segment or 2 segments from the original or from the final polygon. So then you just backpropagate using the data that you've retrieved or that you stored for those particular points. And that gives you the derivative with respect to the original points from the original polygons. So you don't actually have to differentiate through the entire algorithm. In contrast, to take the sign distance, we developed a new algorithm for computing the sign distance for an arbitrary simple polygon. Because the algorithms that we found in the prior work were not robust when you were on the edge. Because we care about it being differentiable and smooth as you move across the boundary from inside and out to outside the polygon. This is shown in the supplement. You can find it on our project website. Yeah, so then what you can do is you can plug this into any sort of optimization problem, any sort of numerical solver that you have. by just adding it as an additional penalty term. So maybe you want to optimize, like, keep all the shapes close together, but keep them disjoint. You add this Minkowski term as a penalty, and then you maintain whatever objective you had before. In particular, in our practice, we use an exterior point method with LBFGS guided by line search, where we just progressively stiffen these Minkowski penalties and then keep the objective term the same. And this works really well for a lot of vector graphics problems that we've dealt with in practice. It has a lot of really nice properties. So in particular, if you have a random initialization of all the shapes, very infeasible, you can just run our optimization algorithm, and then you get to something that looks really nice like this, where it satisfies all the constraints. If you have some objective here, like this one tries to keep the triangles close to equilateral, it works really nicely. Even if the problem is actually not feasible at all, then it will still fail in a graceful way. So in this case, for the S that's full of all these other letters, we try just progressively adding more and more letters. And even though it can't actually satisfy the constraints, it still keeps them roughly into the shape. So you can still really easily make out the fact that it is supposed to be an S. So that gives a couple of examples. Jiří is going to explain some more applications of our work in other settings.
Yeah, as Sam said, now it's time for fun stuff. So we will show some examples and applications. As you have seen, the optimization problem is defined very generally. So we can basically optimize any energy and any objective function. So here are some nice examples. On the first one, you can see example where we minimize the elastic energy of curve, which leads to nice smooth shape. And while doing that, we also keep all of the shapes and the scenes non-overlapping and inside the circle. The second example shows automatic layout of graph using spectral graph energy. And again, while minimizing this energy, we keep all of the node geometry, which is just different rectangles here, non-overlapping. So this is usually done in other graph layout software as a post-processing step, but here we do everything at once. And finally, we can also do some fun examples like this T-SNE embedding of fonts, where we keep all of the labels non-intersecting, and we can also add additional constraints like this hole in the middle. Now again, since we can basically minimize any energy, we can use this for applications not just in vector graphics. So here is a classical problem from computational geometry, where we want to find some nice-looking 2D projection of some given 3D mesh. And we basically want to have the least amount of distortion of this projection while keeping it injective, meaning there is no self-intersection. And with our method, you can also add additional constraints, like here on the bottom left. And it also works on this bottom right example with a sharp corner where some other methods fail. Now more straightforward application in vector graphics. So say you have these two vector assets, and you really like the shapes of the organelles from the first image, but you like the cell shapes from the second one. So with this method, you can automatically find nice packing of these organelles, which is non-overlapping, and you can put them into these new cell shapes. And also, you can just randomize the initial condition to get a variety of different examples. And finally, a really nice application in automatic creation of mathematical and other diagrams, where we actually implemented Minkowski penalties for some simple shapes like rectangles, circles, and lines in open source software called Penrose. And in Penrose, you can create beautiful diagrams like these just by writing simple mathematical notations. So for all of these examples, Minkowski penalties were used in some way. So thank you.